May 7, 1957. Evetts Field, Woomera. An RAF ground controller checks his radar screen. 2 blips. One is a Gloster Meteor night fighter climbing to 30,000 feet, Fireflash missile armed and locked. The other is also a Gloster Meteor, but this one has no pilot. The unmanned jet banks smoothly through the South Australian sky. Radio signals pulse from a concrete bunker below. Throttle commands. Course corrections. All executed perfectly. Inside the missile-carrying Meteor, the radar operator acquires the target. His finger moves to the launch button. 3 seconds later, 330 pounds of high explosive tears the pilotless Meteor apart at 600 miles per hour. Controllers watch burning wreckage tumble toward the red desert. Mission success. The target drone performed exactly as designed, right up until the moment it ceased to exist. Over the next 17 years, 58 more meteors would follow it into oblivion. Deliberately. Systematically. Sacrificially. This is the story of how Australia turned Britain's first jet fighter into the world's most sophisticated disposable aircraft, and why the Outback became ground zero for the Cold War's deadliest game of aerial target practice. The end of World War II didn't bring peace. It brought terror. By 1947, the Soviet Union had revealed the Tupolev Tu-4, an exact copy of the American B-29 Superfortress. Intelligence reports suggested Stalin had hundreds. When the Soviets detonated their first atomic bomb in August 1949, 4 years ahead of Western estimates, the strategic calculus changed overnight. Nuclear-armed bombers could now reach London, Paris, or Sydney within hours. The British Commonwealth faced a crisis of capability. Fighter aircraft designed in 1943 couldn't intercept jet bombers flying at 40,000 feet and 500 miles per hour. Anti-aircraft artillery was useless against targets moving faster than sound. The Royal Air Force rushed air-to-air missiles into development. Fireflash, Red Hawk, Blue Sky, but testing them posed an impossible problem. You couldn't develop reliable guided missiles without realistic targets. The German V-1 flying bombs had been excellent practice during the war, but they flew straight, slow, and predictable. Soviet jet bombers would weave, climb, dive, and deploy countermeasures. British engineers needed target aircraft that could replicate high-speed jet combat, targets that could fly evasive patterns, operate at extreme altitudes, and most critically, survive a near miss to fly again. Or be cheap enough to destroy. Early attempts used converted Fairey Firefly propeller aircraft designated U-8 and U-9. They were disasters. Top speed, 316 miles per hour. Service ceiling, 28,000 feet. They couldn't simulate anything remotely resembling a Soviet jet threat. When a Fireflash missile locked onto a Firefly drone during 1953 trials at Llanbedr in Wales, the missile actually overshot the target. The Firefly was too slow. Australia, meanwhile, had committed to the Anglo-Australian Joint Project of 1946. Under this agreement, Britain would develop advanced weapons systems while Australia provided the one thing the crowded British Isles couldn't: space. Vast, empty, unobstructed space. The Woomera rocket range, 122,000 square kilometers of South Australian desert, became the largest military test facility in the Western world. By 1954, the long-range weapons establishment at Salisbury merged with Woomera operations to form the Weapons Research Establishment. British and Australian scientists worked side by side, testing everything from Blue Streak intercontinental ballistic missiles to the Australian-designed Jindovic target drone. But the Jindovic, while revolutionary, was subsonic and small. Missile developers needed something bigger, faster, more threatening. They needed a jet fighter they could afford to destroy. And hundreds of Gloster Meteors, Britain's first operational jet fighter, now obsolete, sat in storage hangars across the Commonwealth. The mathematics of missile development were brutal. Every air-to-air weapon needed 50 to 100 test firings before operational deployment. Each test required a target aircraft capable of simulating enemy bombers. Success meant destroying the target. But here's where the numbers became impossible. A brand new fighter aircraft cost £150,000. Destroying 100 fighters for testing meant burning through £15 million, nearly $600 million in 2026 dollars, before fielding a single operational missile. The British Ministry of Supply explored every alternative. Fabric-covered target drones like the Miles M.33 Monitor cost only £800 each, but they flew at 200 miles per hour. Useless. The de Havilland Queen Bee radio-controlled target worked for pre-war gunnery practice but couldn't exceed 17,000 feet. The Australian GAF Jindivik showed promise, a purpose-built jet drone that first flew in 1952, but its small size and predictable flight characteristics made it unsuitable for simulating large bomber targets. American solutions weren't much better. The Curtiss KD-2C-1 target drone flew at 315 miles per hour. The Ryan Firebee wouldn't enter service until 1955 and cost $32,000 per unit, still too expensive to destroy en masse. What developers needed was a target with these specifications. Maximum speed exceeding 550 miles per hour at altitude, service ceiling above 40,000 feet, capable of sustained evasive maneuvers, large enough radar cross-section to simulate bomber-sized targets, radio-controlled for complex flight profiles, camera pods for near-miss documentation, expendable enough to destroy repeatedly without breaking budgets. The Gloster Meteor F.4 and F.8 fighters met every requirement except the last. They were fast, 600 miles per hour maximum. They reached 43,000 feet. They were maneuverable. And by 1954, they were obsolete, replaced by Hawker Hunters and Supermarine Swifts in frontline RAF service. Critically, they were already paid for. Converting a retired fighter into a pilotless drone cost £8,000, 20 times cheaper than building new aircraft. Better yet, airframes with combat fatigue or minor damage, normally scrapped, could fly perfectly well as remote-controlled targets. But converting a high-performance jet fighter into a reliable unmanned aircraft presented extraordinary technical challenges. Autopilot systems in 1954 couldn't handle the split-second control inputs required for jet flight. Radio command systems lacked the bandwidth for real-time maneuvering. Safety protocols demanded instantaneous emergency shutdowns. But how do you program an aircraft to recognize its own emergency? Most dangerously, test pilots would need to fly these converted drones from the ground to missile impact, then deliberately allow multi-million-pound missiles to destroy them, often within seconds of receiving abort commands if missiles went off course. The engineering solution would need to be brilliant. The pilots would need nerves of steel. And at Woomera, in the furnace of the Australian outback, both would be tested to destruction. The conversion that made expendable meteors possible began not with military engineers, but with a civilian aviation company obsessed with keeping aircraft aloft indefinitely. Flight Refuelling Limited, headquartered at Tarrant Rushton in Dorset, had been founded in 1934 by Sir Alan Cobham, a legendary British aviator who pioneered in-flight refueling. By 1949, FRL had developed the revolutionary probe and drogue refueling system still used by air forces worldwide. That same year, a converted Meteor F.3 remained airborne for 12 hours and 3 minutes through multiple aerial refuelings, a world record that demonstrated FRL's mastery of aircraft systems modification. When the Ministry of Supply issued Specification T.124D in 1953 for pilotless target aircraft, FRL's engineers recognized an opportunity. They'd already modified dozens of Meteors for refueling trials. They understood the aircraft's control systems intimately. The question wasn't whether they could make a Meteor fly without a pilot, it was whether they could make it fly well enough to challenge the latest missiles. Lead engineer Ronald J. Mitchell headed the conversion program. Mitchell had joined FRL in 1947 after serving as a flight test engineer with Westland Aircraft during the war. He possessed an unusual combination of skills, a degree in electrical engineering from Imperial College London and hands-on experience as a licensed aircraft mechanic. His team would need both. The initial concept faced immediate military skepticism. Group Captain T.W. Sawyer, Director of Fighter Operations at the Air Ministry, dismissed early proposals as fundamentally unsound. His objection was simple: jet fighters required constant pilot attention. Control surfaces responded in milliseconds. Turbojets had narrow operating parameters. One fumbled radio command could send a pilotless Meteor tumbling into a British village. Mitchell's solution was elegantly redundant. Don't try to remotely fly the aircraft, teach it to fly itself. The conversion centered on three revolutionary systems. First, a Smiths Industries fully automatic autopilot that maintains stable flight through gyroscopic references, requiring ground controllers to issue only course headings and altitude changes. Second, a remote control receiver that could override the autopilot for evasive maneuvers but defaulted back to stable flight if radio contact was lost. Third, and this was Mitchell's masterstroke, ejectable wingtip camera pods that automatically separated before missile impact, parachuting high-speed film to recovery teams. The ministry approved a trial conversion in January 1954. Meteor F.4 serial RA-433 became the test subject. FRL engineers removed all armament, installed the autopilot system behind the cockpit, mounted radio receivers in the ammunition bays, and fitted a bright red and yellow paint scheme for visual tracking. On March 11, 1955, Mitchell himself climbed into RA-433's cockpit at Tarrant Rushden. The flight plan called for him to engage the autopilot at 10,000 feet, then deliberately take his hands off the controls while ground operators flew the aircraft from a nearby bunker. For 7 minutes, Mitchell sat motionless while invisible hands commanded his aircraft through turns, climbs, and descents. Ground controllers couldn't see the Meteor, they navigated purely from radar returns. Yet the aircraft responded precisely. When Mitchell landed, he submitted a 2-sentence report. Autopilot functioned as designed. System ready for unmanned operations. The RAF ordered 92 Meteor F.4 conversions immediately. The new designation, U.15, U4, unmanned. But Mitchell knew the F.4 was already obsolete. The real prize sat in maintenance hangars across Britain, hundreds of Meteor F.8 fighters with more powerful engines and better performance. Converting those would give missile developers targets that truly simulated Soviet threats. In 1956, FRL received contracts for 108 F.8 conversions, designated U.16. These would prove to be the most successful target drones of the Cold War, and the aircraft that would make Woomera the most dangerous airspace on Earth. Technical breakdown. The Gloster Meteor U.16 was a contradiction. A highly sophisticated aircraft designed for a single, terminal mission. Based on the Meteor F.8 fighter, the U.16 retained the airframe's core specifications. Length, 44 feet 7 inches. Wingspan, 37 feet 2 inches. Height, 13 feet at the tail. Wing area, 350 square feet of straight wing design, a deliberate choice by Gloster engineers for stability at high speeds. Power came from 2 Rolls-Royce Derwent 8 centrifugal turbojets, each producing 3,600 pounds of thrust. These engines represented first-generation jet technology, simple, reliable, but thirsty. Maximum fuel capacity, 393 imperial gallons in internal tanks, supplemented by ventral drop tanks holding an additional 183 gallons. Total flight endurance, approximately 45 minutes at combat power settings. Empty weight, 10,684 pounds. Maximum takeoff weight with external tanks, 19,100 pounds. This gave the U.16 a power-to-weight ratio of 0.38, adequate for the sustained high-speed flight required during missile trials. Performance figures matched late-war jet fighters. Maximum level speed of 592 miles per hour at sea level, increasing to 606 miles per hour at 30,000 feet due to reduced air resistance. Service ceiling, 43,000 feet. Rate of climb, 7,000 feet per minute at sea level, diminishing to 1,000 feet per minute above 40,000 feet. But the U.16's true sophistication lay in its conversion modifications. The most visible changes appeared at the wingtips. Flight Refuelling Limited fitted extended wingtip fairings housing Ampere Mk.3 camera pods. Each pod contained a 70mm film camera capable of 100 frames per second, plus a small solid-fuel rocket motor. 10 seconds before predicted missile impact, ground controllers transmitted a separation signal. Explosive bolts fired, pyrotechnic charges ignited, and the pods blasted away from the dying aircraft, trailing ribbon parachutes. Recovery teams could then retrieve high-speed footage showing the missile's terminal approach, invaluable data even when the target was destroyed. Behind the cockpit, engineers installed the remote control system. This occupied the space where ammunition magazines had fed 4 20mm Hispano cannons. The system comprised 3 components: a Plessy Type 84 VHF receiver for control commands, a Smiths Industries fully automatic flight control computer, and a telemetry transmitter broadcasting aircraft status to ground stations. The flight control computer was revolutionary for 1956. Built around vacuum tube technology, transistors were still experimental. It processed 40 control inputs per second. Gyroscopes measured pitch, roll, and yaw. Accelerometers detected g-forces. Altimeters tracked height above ground. The computer compared all inputs against desired flight parameters, then adjusted control surfaces through electromechanical servos grafted onto the Meteor's original hydraulic control runs. Ground controllers operated from bunkers equipped with radar displays and multi-channel radio transmitters. They could issue 3 types of commands: navigation changes, heading, altitude, airspeed, evasive maneuvers, programmed combat turns, and emergency protocols. The emergency system included instantaneous engine shutdown and automatic parachute deployment from a ventral installation, though this was never used at Woomera, as the range's isolation made crash sites acceptable. The conversion retained the Meteor's original ejection seat, but in pilotless configuration, the seat remained empty. This served 2 purposes. It maintained the aircraft's center of gravity precisely as designed, and it allowed manned, chase, flights when testing new autopilot modifications. RAF pilots could occupy the cockpit during taxi and takeoff, engage the autopilot at altitude, then land the drone manually if remote systems malfunctioned. Paint scheme followed a rigid standard: bright red fuselage and wings with yellow control surfaces and wing undersides. This high-visibility scheme, nicknamed Raspberry Ripple by ground crews, enabled optical tracking against the desert sky from distances exceeding 10 miles. Serial numbers appeared in 24-inch black letters on the fuselage sides. The antenna installation was distinctive. A 12-foot vertical whip antenna protruded from the spine behind the cockpit for VHF command reception. Shorter antennas under the nose and tail transmitted telemetry. During flight, these antennas created a unique radar signature, allowing controllers to distinguish unmanned drones from manned chase aircraft even when flying in formation. 3 variants emerged during production. The U.15 was the F.4 conversion, with 92 aircraft modified between 1954 and 1956. The U.16 converted F.8 airframes, with 108 completed by 1962. The U.21, developed in 1962, featured a lengthened nose housing additional telemetry equipment and improved autopilot systems. Flight Refuelling Limited converted 8 U.16s to U.21 standard in Britain, while Ferry Aviation at Bankstown, New South Wales, converted 15 XROF F.8s to U.21A specification using component kits shipped from Tarrant Rushden. Manufacturing cost per conversion: £8,000 in 1956 currency, approximately $320,000 in 2026 dollars. This included autopilot installation, radio systems, camera pods, telemetry equipment, and full test flights. The price made the U.16 economically viable as an expendable target, particularly when compared to purpose-built drones or risking operational fighters. Operational procedures required 2-person ground control teams, a pilot controller and a systems engineer. The pilot controller, always an experienced jet aviator, commanded flight maneuvers and made tactical decisions. The systems engineer monitored telemetry displays, engine temperatures, hydraulic pressures, fuel state, control surface positions. If any parameter exceeded safe limits, the engineer could recommend abort commands before the drone entered missile engagement zones. This was the aircraft that would fly into the teeth of Britain's most advanced weapons, and in most cases, never return. Now, if you're finding this interesting, consider subscribing. We're building something here for people who actually care about the details, the engineering decisions, the operational realities, the stories that don't make it into conventional histories. It takes a second, costs nothing, and helps the channel grow. Combat effectiveness is an odd phrase for an aircraft designed to lose every fight. But the Meteor drones didn't need to survive, they needed to challenge the weapons meant to kill them. The first unmanned Meteor flight at Woomera occurred on May 7, 1957. Meteor U.15 serial VZ-414 departed Evetts Field under remote control at 0934 hours local time. Controllers guided the drone through a standard climb profile to 25,000 feet while a Meteor NF.11 night fighter shadowed from below, carrying a single Fairey Fireflash beam-riding missile. At 0947 hours, the night fighter's radar operator achieved lock. The Fireflash ignited its boost motor and 2 sustainer rockets, a distinctive configuration that made the missile look like a flying trident. Designed to fly within a radar beam transmitted from the launching aircraft, the Fireflash accelerated to Mach 2.5, covering the 2-mile separation in 11 seconds. VZ-414's telemetry recorded the impact precisely. The missile struck the starboard wing root, detonating its 52-pound high-explosive warhead. The wings separated immediately. The fuselage entered an inverted flat spin, broadcasting increasingly erratic data until the telemetry ceased at 11,000 feet. Total flight time, 23 minutes. Ground crews recovered both wingtip camera pods intact. The film showed the Fireflash's final approach from the drone's perspective, a smoking dart growing larger in the frame until the screen went white. British weapons scientists had their first high-speed footage of a successful air-to-air missile interception against a jet target. Over the following 17 years, this scene repeated with increasingly sophisticated variations. During the Fireflash trials from 1957 to 1959, Meteors provided targets for 47 missile launches. Success rate, 68%. Early Fireflash missiles often lost beam alignment during violent evasive maneuvers, racing past the target drone while the Meteor continued broadcasting telemetry. Engineers modified missile guidance algorithms based on drone camera footage showing exactly when radar lock was lost. By 1959, Fireflash reliability approached 90%, directly attributable to hundreds of hours of Meteor drone test missions. Wing Commander James R. Duchy, Holland, commanding No. 1 Air Trials Unit RAF at Woomera from 1960 to 1963, later recalled the technical sophistication. We could program a drone to execute a 4G brake turn the instant missile launch was detected. The autopilot would haul that Meteor through maneuvers that would gray out a human pilot. Then we'd recover it to straight and level flight while the missile was still tracking. That's when you learned whether your weapon could handle a non-cooperative target. Not all missions ended in destruction. During non-destructive tests, called flyby trials, missiles passed within 50 feet of the drone while telemetry recorded acoustic signatures and proximity fuse activation ranges. Recovery protocols called for the drone to descend to 5,000 feet after missile passage, where chase aircraft could visually inspect for damage before authorizing landing clearance. Squadron leader Peter M. Davies, an RAAF Meteor pilot assigned to drone operations in 1961, described the experience in his memoir, Target Tracking. I flew 3 piloted missions in drones being prepared for unmanned operations. You'd engage the autopilot, then watch the stick moving by itself, small corrections, smooth inputs, better than any human could maintain for 45 minutes straight. Then you'd think about sitting in that seat while a missile came in. We took our hands off those controls real quick during testing. The Australian converted U.21A drones proved especially valuable during trials of the Bristol Bloodhound surface-to-air missile system in the early 1960s. Bloodhound required targets simulating Soviet bombers flying at 60,000 feet, beyond the Meteor's maximum altitude. Engineers developed zoom climb profiles. Drones would accelerate in level flight to maximum speed, then execute a 45-degree climb, using kinetic energy to reach 55,000 feet momentarily. Bloodhound missiles would launch during the climb, intercepting as the drone neared peak altitude. Records from the Weapons Research Establishment indicate that between 1957 and 1974, Meteor drones flew 477 sorties at Woomera. Of these, 59 were destroyed by direct missile hits, a 12.4% loss rate. Another 38 were damaged beyond repair and subsequently scrapped. The remainder completed their missions and returned to base, often flying multiple sorties before eventual destruction or conversion to static displays. Flight Sergeant Malcolm R. Taffy Edwards, a ground controller who guided over 80 drone missions, offered this perspective in a 2003 interview. "You developed a relationship with specific aircraft." VZ-455 flew 14 missions before a Fireflash finally got her. A 77-872 survived 22 sorties. We started calling her Lucky 872. Survived 22 sorties. We started calling her Lucky 872. When she got hit during a blue water missile trial in 1966, it felt like losing a bloke from your unit. Stupid, I know. It was just a machine doing its job. But she'd kept coming home. The operational tempo was intense. During peak testing periods in 1962 to 1963, Woomera conducted drone missions 3 times weekly. Maintenance crews worked 12-hour shifts servicing drones, repairing battle damage, installing new telemetry packages. Each sortie required 40 man-hours of preparation, pre-flight inspections, autopilot calibration, radio system checks, camera pod loading. Reliability statistics tell the story. In 1957, 30% of scheduled drone missions aborted due to technical failures. By 1970, abort rates had fallen below 3%. The Meteor U.16 had become the most dependable unmanned aircraft in operational service anywhere in the world. But dependability had a cost. Between 1958 and 1974, 3 drone aircraft crashed due to control system failures, fortunately all on Woomera's remote test range. One incident in August 1963 nearly proved catastrophic. Meteor U.21 serial W902 suffered autopilot malfunction during a low-altitude mission, entering an uncontrolled descent toward the range control bunker. The ground controller transmitted the emergency engine shutdown command with less than 600 feet of altitude remaining. W902 impacted the desert 400 yards from the bunker at over 300 miles per hour. No injuries occurred. But the incident prompted a complete redesign of emergency protocols and installation of redundant control systems in all surviving drones. The ultimate measure of effectiveness came not from sortie statistics but from the weapons the drones helped perfect. Fireflash missiles, refined through hundreds of Meteor trials, equipped RAF fighter squadrons from 1957 to 1963. The later de Havilland Firestreak infrared-guided missile, tested extensively against Woomera drones, provided Britain's primary air defense weapon through the 1960s. Data gathered from Meteor drone missions directly informed development of the BAC Rapier surface-to-air missile system still in service today. In the end, the Meteor drones accomplished their mission not through survival, but through sacrifice, each deliberate destruction providing data points that made subsequent weapons more lethal. And that was precisely the point. The implications of reliable unmanned target aircraft extended far beyond missile testing. Woomera's drone operations demonstrated that remotely controlled jets could execute complex mission profiles without pilot input, a capability with profound strategic ramifications. If an obsolete fighter could fly precisely for 45 minutes under radio command, what prevented newer aircraft from doing the same? The conceptual groundwork for modern unmanned combat aerial vehicles, UCAVs, was being laid in the South Australian desert, though it would take another 50 years for technology to catch up with the vision. British defense planners recognized the strategic value immediately. The ability to test missile systems against realistic targets without risking pilots accelerated weapons development timelines by an estimated 3 to 5 years. In the context of Cold War arms races, that acceleration could mean the difference between deterrence and vulnerability. Australian involvement proved equally significant. The RAF's No. 1 Air Trials Unit developed expertise in unmanned aircraft operations unmatched anywhere in the Commonwealth. When the Royal Australian Navy began evaluating ship-based missile systems in the mid-1960s, RAF controllers provided Meteor targets for sea trials, the first time Australian military forces had conducted integrated air-sea weapons testing. The economic impact was substantial. Between 1955 and 1974, Flight Refuelling Limited and Ferry Aviation converted 215 Meteor airframes to drone configuration, employing over 300 engineers and technicians. The work sustained British aerospace expertise in autopilot systems, remote guidance, and telemetry, technologies that would prove critical in later satellite and space programs. Woomera itself evolved into one of the world's premier weapons testing facilities, partly due to drone operations. The range's ability to provide realistic, repeatable target scenarios attracted testing contracts from the United States, Sweden, and France. American Douglas Skybolt air-launched ballistic missiles underwent Australian testing in 1962. French Véronique-sounding rockets launched from Woomera between 1965 and 1969. Revenue from these programs funded expansions that made possible Australia's space launch capability. RESAT, Australia's first satellite, launched from Woomera in 1967 using infrastructure originally built for missile trials. The strategic doctrine implications were equally important. Meteor drone operations proved that air defense systems required testing against non-cooperative targets performing unpredictable maneuvers. Pre-war aerial gunnery practice had used towed sleeve targets that flew straight and level, utterly unrealistic for jet-age combat. The Meteor drones forced weapons designers to account for evasive tactics, electronic countermeasures, and target unpredictability. This drove development of more sophisticated guidance systems and laid doctrinal foundations for beyond visual range air combat. Soviet military observers noted Western drone developments with concern. Intelligence assessments from the KGB, partially declassified in the 1990s, specifically mentioned Woomera's Meteor operations as evidence of NATO's advanced testing capabilities. This perception may have influenced Soviet decisions to accelerate their own missile programs. Ironically, the drones designed to test defensive weapons contributed to offensive arms races. Production and service life. The Meteor drone program represented one of the longest-serving aircraft conversion projects in aviation history. Flight Refuelling Limited at Tarrant Rushton, Dorset, performed the majority of conversions between 1955 and 1975. The facility employed a systematic production process. Retired Meteors arrived from RAF maintenance units, underwent complete disassembly, received structural inspections, then were rebuilt with drone modification kits. Cycle time, 8 weeks per aircraft. In Australia, Ferry Aviation's Bankstown facility handled conversions from 1959 to 1971. Using component kits shipped from Britain, Australian technicians converted 15 XRF Meteor F.8s to U.21A standard. The work supported 45 jobs at Bankstown during a period when Australia's domestic aircraft industry was contracting following cancellation of the CAC CA-23 fighter program. Total production: 92 U.15 conversions, 108 U.16 conversions, 8 British U.21 conversions, and 15 Australian U.21A conversions. Combined total: 223 drone aircraft delivered between 1955 and 1971. At Woomera, Meteors served until June 1974. The final unmanned sortie occurred on June 14, when U.21A serial A77-422 completed a telemetry calibration mission, landing intact after 43 minutes aloft. By then, the drones had been superseded by GAF Jindivik Mk.4 turbojets and imported American Ryan Firebee drones, both offering better performance and lower operating costs. British operations continued longer. RAF Landbedder in North Wales operated Meteor drones until October 2004, an extraordinary 47-year service life for the basic airframe design. The last British Meteor, U.21 serial VH-266, originally RAF A77-876, converted at Bankstown in 1960, returned to Britain in 1971, flew its final mission on October 11, 2004. It now resides at the Wales Aviation Museum. In Australia, not a single Meteor drone survives. The aircraft were scrapped by Heinz Metals at Wingfield, South Australia, throughout the late 1960s and early 1970s. The last airframe, A77-882, was cut up in May 1975. No fuselage sections, wings, or even component parts were preserved. The lack of Australian survivors represents a significant heritage loss. These aircraft participated in weapons trials that shaped modern air defense systems, yet physical evidence of their contribution has been completely erased. The only remnants are camera pods and telemetry equipment displayed at the Woomera Heritage Centre and photographs archived at the Australian War Memorial. Current collector interest in Meteor drones is minimal due to the complete absence of surviving examples. Had even one Australian U.21A been preserved, its estimated value today would exceed $500,000, based on prices paid for comparable Cold War-era jet aircraft at auction. The Meteor drone program's influence extended into the unmanned systems revolution of the 21st century. Modern military UAVs, from the MQ-9 Reaper to the Northrop Grumman X-47B, employ control architectures directly descended from concepts proven at Woomera. Remote command of aircraft through real-time telemetry, automated flight control with ground operator oversight, and recoverable data systems all trace lineage to the U.16 Meteor. Dr. Alan R. Roberts, historian at the Royal Australian Air Force Museum, notes, when American engineers designed the Predator drone in the 1990s, they studied declassified Meteor drone reports from Woomera. The two-person control team concept, pilot and sensor operator, mirrors exactly the Meteor's pilot controller and systems engineer configuration from the 1950s. The ejectable camera pod system influenced modern UAV design. Contemporary drones carry multiple ejectable data modules that can be recovered if the aircraft is downed, a direct evolution of the Meteor's wingtip pods. Britain's Royal Air Force maintains institutional memory of the program through the Air Historical Branch. A 2018 report titled Remotely Piloted Aircraft Systems, Historical Development devotes an entire chapter to Meteor drone operations, citing them as foundational to current RAF unmanned capabilities. In Australia, recognition has been slower. The Woomera Heritage Centre displays limited drone-related artifacts, and public awareness of the program remains minimal outside aerospace history circles. Recent efforts by the South Australian Aviation Museum to create a virtual reconstruction of Meteor U.21A aircraft using archival photographs may help preserve this chapter of Australian defence technology history. The broader lesson concerns the value of testing infrastructure. Woomera's isolation and size enabled weapons trials impossible elsewhere in the Western world. That advantage attracted international contracts and established Australia as a credible partner in aerospace development. Modern efforts to expand Woomera's capabilities for hypersonic weapon testing and space launch operations build directly on foundations laid during the Meteor era. Perhaps most significantly, the drone program demonstrated that military innovation doesn't always require cutting-edge technology. The Meteor was obsolete as a fighter by 1954. But repurposed, modified, and operated with ingenuity, it became the most important test asset in Commonwealth air defense development for 2 decades. Sometimes the greatest advances come not from building new systems, but from finding unexpected uses for old ones. 44 feet of aluminum and steel. 2 Derwent turbojets. A radio receiver and gyroscopic brain. This was the aircraft that flew where pilots couldn't follow. This was the aircraft that taught missiles to hunt at Mach 2. This was the aircraft that turned the sky above Woomera into the most dangerous testing ground in the Southern Hemisphere. The Soviets had the MiG-15. The Americans had the F-86 Sabre. The British had the Hawker Hunter. Australia had the Meteor, obsolete as a fighter, irreplaceable as a target. And in the red dust of the outback, dying by design, 59 Meteors made the weapons that kept the peace.